Okay, good morning in Switzerland and good evening in Japan. Welcome to the fifth round of EPFL CIS and RIKEN AIP joint seminar series. So my name is Masashi Sugiyama. I'm from the RIKEN side. So today I give a short introduction before starting the talk. So this is the seminar series. Already we had 4 talks previously, and this is the 5th round. And then actually after today, so we have 3 more sessions are already scheduled in December 15th and on January 19th and February 16th. So we are looking for you to join those events also. Okay, then, so let me introduce our speaker today. So Professor Martin Jaggi from EPFL CIS. So Martin Jaggi is a tenure-track assistant professor at EPFL, heading the machine learning and optimization lab. Before that, he was a postdoc at ETH Zurich, at the Simons Institute in Berkeley, and also at the École Polytechnique in Paris. So he has earned his PhD in machine learning and optimization from ETH Zurich in the year 2011, and then also a Master of Science in Mathematics, also from ETH Zurich. Okay, so we are very grateful to have Martin today. So would you please start your presentation?
Yeah, it's a great pleasure to join for this seminar, and please interrupt anytime if something is unclear. So I will try to share some kind of broad applications here, which are quite different in each use case we discuss. So I'm looking forward to the discussion. I'd like to talk about learning with strange gradients, in the sense that gradients in the training of neural networks, which we are not familiar with. So that's the general theme. The use cases we'll discuss will mostly come from some collaborative learning applications. And what we're trying to do in that setting is really to train a machine learning model on all the data. But the data is kind of split between several participants, as we can see maybe on the bottom. When there's this like 5 participants, they together like to train a machine learning model. But we would like to do this while respecting privacy and also doing this efficiently, so that we obtain the same trained model as we would if we would put all the data in one place, which you can see on the top right, for example. So this includes, for example, federated learning, but also many other settings. So that's the motivation. And the cases I'd like to discuss a bit more are like this. So there are 4 of them. The first one is when these collaborators trying to train together have a bit of different data distributions, which is a realistic case when we learn together. This is the so-called heterogeneous data case. The second case I'd like to discuss is when everyone already has a slightly different objective function they want to learn or they want to train. So that's also called a personalization. And then the third one will be a bit different. So here we will not have necessarily different people which collaborate, but more we have maybe training of one neural network, but also some related smaller neural networks. Can these 2 neural networks help the training of each other, so to say? And then last but not least, I'd like to comment on the robustness. And robustness here is meant again for the training process. So if one of the participants tries to break the system by providing bad data, by providing very strange messages, are they able to derail the training process for the others or not? Or could we build some algorithmic schemes which allow still to achieve robust training? So that's the overview. And the tools we're going to use for this are very standard. We will just use gradient-based methods in this talk here. Of course, there are many other methods as well. We could find other ways to collaborate between 2 agents who want to train something together. But here we're going to restrict ourselves to gradient-based methods. So I usually will be the agent participating here. One agent can have several data points. It will not matter much for our discussion. And then what's important is that the data is partitioned over these devices, so it's local to the current participant. we can compute the gradient, and then we can share it with our collaborators, so we can share it with the cloud. So that's what you can see maybe on the right, where we would compute the update to our parameters x by computing a gradient, say, and then share this update, or maybe a compressed version of it, with others to help the training process. That's the main building block. And the first a bit more concrete application will again be in this federated learning case. So federated learning is formalized a bit like this. So basically what we said, that we have a very large data set, but which is not brought into one place, but the data set remains as it is. It remains partitioned over these clients. So everyone has a small part of the data set, but we really want to respect privacy. We want to allow these participants to keep the data local without ever sending any data out of the machine. So this is the setup. Mathematically, our goal is still to optimize the training objective over all data. So that's the sum over all agents I, which we try to minimize. So we're trying to find one parameter set X, which fits everybody. And that's the goal of the optimization. How do we do this? So the simplest algorithm for it is known as like local SGD, where every client does a few SGD steps on its own. And that's also called a federated averaging in the case of this federated learning scenario here. So how it works is we start at an initial point X. We do here in this case, both of the clients do 3 steps each of applying gradients on the local data and applying them to the local parameters. So here the local parameters are called Y. So everyone optimizes a bit for their own for 3 steps here. After that, the round is finished and the parameters get averaged between everyone again. So this is the communication phase. So that's indicated by the yellow arrows after each round, which we then end up with a new set of parameters here again called X, which are shared with everyone. So then the next round will start, and that's the entire algorithm. This is quite well understood if the data are similar between the clients, if everyone has data from the same distribution, the so-called IRD case. But in federated learning, the one very important assumption is that the data can be different between each client, right? So the Fi might not be the same as the Fj, which we have on the 2 workers here, which is indicated, for example, in this level sets of the blue or green lines. So this would indicate that here's an example where the minimizers of client 1 are very different from the minimizers of client 2. So from this picture, you can already see that there might be a problem if one does too many of these local steps on each client alone. Then they might over specialize. They might converge too far to their own minimizer, but their own minimizer x1 star, it might have nothing to do with the minimizer of the sum. So the global minimizer, which here is written as x star, which might be far away from any of these individual minimizers. But our goal is to solve the global problem, right? The sum of everyone's Fi. So this problem is called client drift. And as we said, it becomes more severe the more different the data is, which is present on each client. So I hope that's clear for the setup. I'm happy to take any questions if you. So if not, we will try to think about some algorithms which could alleviate this problem of client drift, which means that we would just like to converge as fast as possible and see if we can do a speed up, for example. So one way to make this a little bit faster is to use momentum. And so momentum is indicated here with the red arrows. So this is really the same example as before for the same classic algorithm we had, federated averaging. But the difference here is that after the round has completed, we have averaged the parameters, but now we do apply a momentum vector to the result after each round, which is indicated with the red arrow here. So this red arrow is computed globally. After each round, we update also our momentum vector, and we apply it to the global set of parameters x after each round. So this is very popular in deep learning in any case, even if you just train with one computer. And it also makes sense here. So you could ask if this is going to be a bit faster, and it is, but it's not going to solve the main problem of client drift, because you can see even within these 3 steps, the blue worker still has already converged to an over-specialized and too personalized solution. So we have not solved that problem yet simply by applying momentum. One idea, which is a very simple modification of this, is to basically do the same thing. We compute the momentum vector in exactly the same way after each round, but the difference is here that we apply it much more often. So the momentum is not only applied after each round, but it's applied immediately after every small local iteration. So each of these 3 small steps, an amount of the momentum correction has already been applied. So whenever the workers do something local, which is the blue or green arrows, they immediately correct it by this global vector, which is the red one from the momentum. The good property of the momentum vector is that it's global, right? It's reflective of both data sets, not only one of them. Whereas the blue and green steps, as in contrast, those are client specific, so they are biased for the global objective, which should be all the clients, right? But the red vectors, so that's the idea, those reflect all data, so those might be better. They're kind of a correction to better adapt the blue vectors to be useful for the global problem, which is the sum of everyone's objective. So this is the general theme. And again, so what we have done is we have kind of found a way to correct these kind of strange gradients from the blue and green ones. We have found a way to correct them and make them more useful for the global objective. That's how this would fit in the team. And this framework here is called the Mime algorithm, because it mimics the centralized algorithm. So centralized would be that if every data would be in one place, then the problem would be easy. So we would actually like to have an algorithm in the federated case which behaves like the centralized one. So that's why this is the team applying here, and it works for any algorithm which you might already have. If it uses momentum, you can just apply this trick, compute momentum globally, but apply it locally, and then you have obtained a federated algorithm for the same original centralized method. So mathematically, this is what it is. It's basically just as we said, you have standard local steps happening. Again, the local parameters would be called y. Every local steps, they are already corrected with the global m vector. And then after each round, the m vector is updated as well. Here, to be completely honest, there is one more additional communication needed and one more full gradient which has to be computed after each round in the variant which we do theoretically analyze to update the momentum vector. But this is particularly useful when you have several local steps, very heterogeneous data, and a lot of workers participating. So how to analyze this theoretically? We would like to also compare to other methods here. So we use kind of standard assumptions here. We use the assumption that the objective functions are smooth, so Lipschitz gradients. This is allowing non-convex optimization as well, but we're not going to a global optimizer, but we just go to a stationary point. We go to somewhere x where the gradient is flat, so to say. How many steps do we need to achieve that? Some known baselines methods such as scaffold, they require something like this. So the leading term of Lipschitz constant over epsilon looks correct. And here there is also dependence on n, the number of clients, and s is the number of clients which are active in each round. Maybe not all the millions of phones they answer back every round. So what you do in federated learning, that you subset a set of the active clients in each round. So scaffold is actually interesting because it's also using a very similar idea than we mentioned here. So scaffold is learning it's a variance reduction technique where you learn a control variate vector. For each client, you kind of learn the difference. For each client, you learn the difference. How strange is this client compared to the global gradient? So you learn this difference vector, which is in spirit very similar. It's just that here we use a momentum vector. So we don't need to learn anything. The learning of these difference vectors for each client in scaffold makes it slow down a bit. It makes it that for each client, you need to see that client many times until you have a good estimate of the difference vector, which explains the how this particular client relates to the global gradient. So that's why we have a dependency on n here, which is not optimal, and which we can get rid of when we use this simpler scheme here, which is the Mime scheme, which I described. Here, this needs a bit of explanation. So these rates again look a bit like the usual SGD rates we are familiar with in the single client case. There are some differences. So what's important here is the variances we have between gradients as usual. But here there's two kinds of variances. So one variance is how do my gradients differ from the expectation on each machine. So if you just look at one client individually, within that client, how different are the gradients? So that's the intra-client variance, which is sigma as usual. But then there's another variance of between the clients. So between two workers, what is the variance? So this is just expected Euclidean norm difference of gradients from one client to gradients from another client. So that's the zeta factor. So those two together, sigma and zeta, they describe the variance in gradients. So this is okay, but then there is one more important term, which is the delta. So delta, naively, you can just think of it as L. Then you have the easiest comparison to the scaffold method, so the smoothness constant. But the sigma actually the delta can actually be an even smaller constant because we use another definition here. We use the Hessian similarity between different clients. So this is the variance you have where you look at one Hessian from client one. So this is deterministic, and another Hessian from another client. How different are they? And you can imagine that this difference is always bounded by the smoothness, right? When the gradients change slowly, also the Hessian difference is bounded. So delta is always smaller than L. So that's why the rates for the Mime framework are better than the ones we have for scaffold, if you have a lot of clients N, which is the case we are most interested in here. So also there's two variants of Mime. I didn't explain this in detail. One of them is the theoretical one, which needs this additional full gradient, which is on the bottom line, if you want to get the best theoretical rate. And the other one is the top one is actually what I described to you in the previous slide, which is the one which is simpler to implement, which has a slightly worse dependency on some of the parameters, such as how many clients we sample in each step, which is S. Okay, so why is this good or bad? We will compare these two lower bounds as well. And here the lower bound is from the server alone. There's no collaboration happening. The server just centralizes all data and trains alone. So this, of course, is a comparison. And there it's actually known that you cannot do better than this. So you need as many gradient steps as we have stated on the last line here. Now, this is confusing because the upper bounds we get seem to beat or contradict the lower bound. So the upper bound is better than the lower bound. How is this possible? So especially when delta is much smaller than L, right? Then we beat the lower bound. And this is only possible because we use many local steps, right? Because the server algorithm will only use one local step, so there we cannot count the number of steps. But in the green algorithms, in the federated case, we count the number of rounds, number of communication rounds. And so what this shows is that, yes, so you can have a few communication rounds, and within those rounds, you do benefit from having more than one local step. So in each communication round, the federated methods use many local gradients. So maybe 10 or so to, and what you show here is that, yes, these local gradients, they do get progress, even if they're biased, right? So they're much cheaper to do, they require no communication, but they are biased to the local objective. But here we do see they still do benefit the global objective. How many local steps do we need? It's usually about L over delta for the theoretical purpose, at least. So this is for federated learning with heterogeneous data. And again, the delta and the zeta here describe how different are the clients from each other. So this was the first use case. Is there any comment question on this? If not, I would move to the second case. And this is about personalization. So we again consider collaborative learning, but now we have a different setting that maybe now every client wants to learn a slightly different task. So I think that's a very nice setting as well, because it might be realistic that not all clients want to do the same thing. And on a higher level, this is also part of a nice change that we would like to enable to bring the decisions of that all the options you have as a client to make this a bit more powerful and make this a bottom-up approach instead of a top-down approach. So on the left, you can see that in federated learning, the server decides on anything. The server decides what is being trained, who participates, and so on. On the right, if we try to have a bottom-up approach, then we could ask, would it be possible that the clients themselves, they decide on what they want to train, with whom they want to do it, and when they collaborate. So this would be an ideal situation, I think, when especially when every client also has a different task they want to learn, then I think this would be a much nicer paradigm to have. So this is kind of our goal to enable this, but of course it's not easy. And so, for example, what I want to discuss next is how do we deal with the fact that every user has a slightly different objective function and want to learn something different, and they mainly care about their own task, right? They don't care so much about the other user's task. How do we formalize this mathematically? So it's again very similar to what we had in the federated case when we tried to learn just one global model for everybody, so one X for everybody. Now we have everyone minimizing their own function, so everyone learning the different X, which best fits their own objective Fi for client I. So this is the personalized setting inside of collaborative learning. For us to analyze, it's enough to just consider one client. So this one client F0, what should they do? Who should they exchange gradients with? And most importantly, is it of any benefit to them to actually work with other people's gradients as well? Can it help their objective function? That's the goal. And how do we do this? So the most naive way to actually do something with those received gradients is to just try to use them. We try to average those gradients, and we try to apply them with a small step size to our own objective. So what's happening here is that, of course, we have one gradient from us, which we trust. We computed it on our own data. It fits our task. But then we also receive a whole number of other gradients, which are the gradients from 1 to n. So these are our collaborators, our neighbors. And those maybe are less suitable for us. So some might be, and some, if they're very different, they might be leading to less progress for our objective. So we kind of have to decide on which collaboration weights alpha do we want to use to benefit still from those gradients which we receive. So this is all a collaborative setting. So we assume that users want to help each other, and we try to find good weights alpha, which then do enable that this helping process happens. And yeah, if you look at the formula, you also see that everyone computes the gradients at the same parameter x. So we as user 0, we say, here is our current parameter x, please give us the gradient on this same model x. And then the neighbors will do that, and we have to decide what to do with the gradients received. This is one algorithm and can be analyzed. I'll get back to it. And here is a slightly more advanced version of the same method. What we do here is, again, it's a very similar idea we had in the two cases before. So we see if we can learn a correction, if we can kind of learn for each received gradient I, we can kind of learn how it relates to what we would want to have. We would want to have a gradient for our objective as 0, but we get one from F1. So we're trying to learn a difference vector CI, like this control variate technique, like some of you might know SVRG or so, also scaffold, where you learn this difference vector as you go on, you learn the CI to transform these received gradients to be useful for you in the sense of F0. So here it's just additive correction. So there's two ways we do here. One, we have to decide on the alpha I, and the other one is we have to learn this correction vector or the control variate CI for each of our collaborators. This algorithm will work better, and we will get to it in a second on how much this could help and if you can still analyze this theoretically. In terms of convergence, so now we are just interested in convergence on F0. We don't care about converging on the sum of everybody. So the question is if F0 can optimize more quickly than if they would train alone. And again, the convergence rates look as in usual SGD. How quickly do you get the gradient to become flat? And the rate also looks familiar to those who know. We have smoothness here, L again. F0 is the initial error, so capital F0. Sigma is the variance we have within the client. And then we have 1 over t, so square root of 1 over t is the convergence rate. But the nice thing here is that we do have a speed up of n, the number of collaborators. So the more collaborators you have, the faster you do get to your individual objective. So if you train alone as agent 0, you will have the same conversions, but no speed up with n, right? You only do one gradient at a time. And here you are n times faster if you do benefit from these other collaborators. So this is not giving full details. I have to refer to the paper for all details. What we do here is there is a really simple way to learn the C corrections, and this is just by exponential moving average. So every time you do a step, you get your own gradient and you get all these candidate gradients, and the difference of those, that's what you use as an estimate to improve your CI correction. And then you do an exponential moving average over time to make sure that things stabilize over time to learn the better CIs. I should also say that there are some hidden constants here which go into the step size for this scheme. So there is still there's again going to be a gradient similarity constant here, which is not shown in the rate, but it's going to go into the step size, and it's going to go into the collaboration weights alpha. So if you collaborate with someone who has very similar gradients to you, then you have good gradient similarity, and you will have a larger collaboration weights. You will be able to put more trust in those gradients, so larger alpha, and also larger step size potentially. If someone has a very different gradient, then you might use a smaller collaboration weight, alpha again, and that again will be determined by the variance between the clients in terms of gradients, but also in terms of Hessian. So there's the same parameter of Hessian's dissimilarity delta as we had when we discussed the federated case before, going into the step size and going into the collaboration weight. Okay, this was it for the collaborative learning case. Is there any question or comment? Not so far. Then I would like to switch topic a bit and discuss a very different application. And this is from deep learning, when we try to learn a big network, and maybe we have a small network as well. So can two networks benefit the training of each other? So, and can we also take this from the same viewpoint? Is there an interpretation in terms of gradients from the small network to help the gradients of the big network to make progress on training? So this is illustrated here. So the blue network is the original one you would like to train, and so that's maybe on a powerful device for training on a good GPU or so. But then you also have a small network which might be on a smaller device. So here the smaller network is part of the big one, but it doesn't matter. You could take any two networks you want and just decide that the blue one is the union of the two, and the yellow one is the smaller network. So can these two networks help each other? The setting on the left is called slimmable networks, because it seems to kind of vary the width of these internal layers. So in the big steps, the blue network is a full width, but if you do a step on the yellow network, then it means that these layers have been made much more narrow. So you choose the width of each layer. That's slimmable networks. And then you do a gradient step on the yellow network, which is of course cheaper. And the question is, does it help for the original objective, which is training the blue network? The case on the right, on the very right, is a bit similar. So there we asked the fully connected layers, so can be very expensive and very big. So what you can see on the right here is that the first and last fully connected layers have been kind of replaced by a much smaller version, which is a low rank version of the fully connected layer. So instead of the fully connected one, we just use here a rank 1 version, which means you just add like one neuron, for example, no activation function. And you can see that the yellow network has much fewer weights which need to be learned in that layer compared to the original blue one. So of course you can use a higher rank than rank 1. So how many you add a small number of additional neurons, and that's your cheap version of the original layer. So this is how you can have a low rank version of an original fully connected layer. So how is this going to work? Yeah, by the way, the middle network is just a combination of the two, where you kind of skip some layers sometimes, which is also a way to make it cheaper, like in skip connections, for example. Now we still need to analyze. So what does these gradients have to do with each other? So isn't this that maybe a gradient we get from the yellow network is just a part of the gradient of the big one, right? I could just say, okay, I do a gradient on my yellow network, and that's just going to be whatever, everything I see, we use it, and I think that this is part of the gradient of the blue network. But this is not true, right? It's not computed on the same function. So one has to be careful that it's not just taking a blue gradient and ignoring the parts outside the yellow parts. It's really computing a different function. So what's happening here is that the forward pass is also completely different, right? When we do the yellow network. So when we compute a forward pass there, it means that we have set the weights outside yellow, we have set them to 0. So they are not existent for the current yellow step. So we have made a perturbation to our x, and we compute a gradient on this yellow network on this perturbed point. So we compute the gradient, and then again, it has only entries on yellow. So after we have obtained the gradient from the backward pass, we also mask this gradient, because of course there's no contribution outside the yellow network. So what I'm saying is that this is both perturbing the points where we compute the gradients, and then also masking the gradients themselves, which we obtain. So we have gradients which are computed somewhere else, and which are only covering part of what we used to from the perspective of the blue network. So can we still learn with gradients which are both perturbed and masked? And the answer is again yes. So there is a relation between the two, and I will not give all details here, but the intuition is a bit similar. The intuition is again that if these gradients are similar enough, then they do help us train the blue network faster. And similarity here is measured in kind of the overlap that the gradients have in terms of inner product. But here, as I mentioned, you have to be a bit careful that we define overlap both in terms of the perturbation of position x and in terms of masking of the result. But if these gradients are aligned, which we can observe this alignment in practice in each step, then we do have a speed up compared to training alone on the blue steps alone, which are of course more expensive. So then we do get a benefit from the yellow steps as well. There's also a very nice paper by the group of Dan Alistar, which is simultaneous to ours, which you see on the last line here. And that paper has a very nice bridge of these to the compressed sensing literature, that you can use compressed sensing results if you have restricted strong convexity. You can see that any over-parameterized network actually does have sparse solutions, and therefore you can also analyze the convergence directly using techniques from compressed sensing, which is not what we do, but this is very nice and complementary to this. Okay, so that's what I had when we train different architectures. And how does this fit into the overall team again? Because we found a way to relate these gradients, which are not really what we want, but we found a way to relate them to the task at hand and correct and make them useful for the overall task. And the very last thing I'd like to discuss is the case of robust training. So now we are again back to the collaborative training setting, but now we have the problem that maybe a few actors in this training, they might try to break the system and try to derail the training for everybody. And this will be in the standard federated setting as we had in the very first use case. So it's very simple. Again, everyone sends gradients to the server averages them and sends them back, standard federated learning. But the problem is that maybe some agents are failing. They might compute wrong or not compute anything, so they might return 0. Or some might just be malicious. Some might claim that they have fake data, or they might just send a completely arbitrary message. So that is allowed, and this is the so-called Byzantine adversary setting. So the red adversaries, they have any power you want. They can even collude between each other. They know everything. And then the question is, what message could they send in so that they would break the training process for everybody? Or is it possible to be robust to a small number of such bad agents? And what people have done is to, of course, the point you would try to cope with this is the aggregation when the gradients get added. We we all know that the mean is not a robust estimator. So if just one of the entries, which then gets averaged, if one of these entries is bad, then it can, of course, spoil the entire average. Therefore, instead of the mean, people use something like the median, for example. And the median of these contributions is hopefully a more robust estimator and cannot be influenced too much by one or small number of bad actors. So, for example, you do this coordinate-wise, because here the model, of course, has, these are the weights we are trying to train. There are millions or billions of weights. So we have to apply this for every coordinate separately, for example. And there's many different aggregation rules which have come up in recent years, which try to aggregate these received gradient messages and provide a robustness to still enable training. The problem with these rules is that they had most of the analysis so far were only looking at one step in time. So they were saying that yes, at one time step, we can have a more robust estimator, for example, the median instead of the mean, so that the result was kind of epsilon close to the good result you want in one communication round. But the problem is that over many communication rounds, these errors could add up, and this time aspect was not taken into the account yet. And this slide is just called like this because the paper who proved this kind of attack was called Fall of Empires. There's also another paper which is called Little is Enough, and little is enough is really giving this intuition that I mentioned. So how would you break such a system? As an adversary, you would just in every step make that this epsilon error, which still comes out of this robust aggregation, you would make that this error is always in the same direction, so that over the many steps, the error is accumulated, and then you as an adversary, you can guide in which direction this small error is accumulated over the million steps, and to then guide the training into an arbitrary bad direction. So this is to say that it is not enough to say that the aggregation rule is robust in one step. So we need something which takes time into account. So we can even formalize this to show that no aggregation rule works if you ignore the time aspect. So if you do not use this kind of history aspect to be very careful with what these actors have done in the past, then we cannot avoid this. Then we might completely fail the training, so the training might go to an arbitrary bad point. So we'll not have a convergence result. So we need to fix these aggregation rules to learn from history. So that's the name of our paper, is learning from history. And the way we try to do this is again extremely simple, and it's exactly the same theme as in the previous applications in this talk. We just use momentum to actually account for history. Here we use worker momentum. So every worker will not send only the current gradient G, but it will send this momentum stabilized variant. So you think that the momentum kind of averages over the past steps to kind of smooth things out and make things more stable. And that's exactly the intuition here. And then because everyone not only sends this noisy gradient GI, but a stabilized version, the MI, we have these stabilized estimators from everyone, and those we can aggregate much more reliably, and we can also better detect which ones are good and not, because the MIs are stable and they have less noise. So that's the intuition. So this uses worker momentum, whereas the first application I showed you with collaborative learning, there we used the server momentum actually to compute. The momentum there was computed on the server. Just want to mention this difference here. So here you can ask, when the momentum is computed on the worker or the participant, then how does this work? Because some of the participants might be bad, right? So the bad participants, which are these Byzantine actors, they of course might not do what we write here, right? They can do whatever they want. So how does this work? But this is allowed. So all I'm asking here is that the good workers, which is a substantial fraction of everyone, I only ask that the good workers here apply this worker momentum locally before they then send the M to the server, where we then aggregate them. So that's the only change to the original algorithm. It's very simple. It's just funny that here we don't use momentum to be faster. Here we use momentum to be more stable. So we might use an even stronger momentum to stabilize this estimator so that we can better detect the noise from the signal. So now we receive these momentum stabilized updates M on the server. Now we still need to decide who is good and who is bad. And for that, the aggregation rule is extremely simple. You just use clipping. So there is a center of clipping, and then you just use that everyone has close enough in Euclidean norm counts as a good collaborator, and everyone who is far away, further away than the radius tau here, everyone else is removed. So those you estimate are the bad collaborators you would like to exclude. So this is not perfect. Sometimes you might exclude good collaborators, but the question is how close is this to the truth? And the truth would be, what if only the good collaborators would train together? So can we show a theorem that the convergence from this scheme is similar to the convergence of the good workers alone? So that would be ideal. That's our goal. And by the way, the center of clipping is just the previous model you had on the server. So that's what you can use as your center. And of course, this operation is very efficient, not costing much. And the theorem we have here that is saying that yes, we do converge. We converge to the kind of where we should. So we can converge on the F objective, and here F is the objective only defined by the good workers. So that's what we would like to achieve, and this is also what works here. So what we need for that is that the aggregator needs to be robust. The clipping aggregator, I show you, it does satisfy this robustness property. I have to let the details to refer you to the paper, but this delta and C aggregator, this kind of robustness means the following. It means that if a delta fraction of the actors are bad, then our aggregation rule, it produces something which is kind of only C times worse than if only the good workers would average their results. So that's what it means to be a robust aggregator function. And the clipping operation I showed you, it does satisfy this. So yeah, as we said, we have a delta fraction of the workers are bad. We have, of course, a lot of noise on each worker. And then depending on that noise, we choose more or less momentum to stabilize things. And then we have the convergence to the good optimum. And this is kind of the first global convergence rate, which shows that, yeah, in Byzantine training with some realistic assumptions, yes, we can converge to the same function than we would globally. Well, not just looking at one step being robust, but here you really have a convergence rate over all the steps T. T is the number of steps, and delta is the noise. And is there any question on this? If happy to take a discussion later. So yes, somebody's asking if there's a paper link, and there is, and it's right here. That's on the next slide. Thank you. And this is actually almost bringing us to the end. So here are the papers for the four kind of use cases we discussed. These four use cases of learning with uncommon gradients. Have a look here. And with that, I would like to thank my collaborators. So these papers are mostly joint work with Praneet from our group and Sebastian, and also other people from our group. Thank you very much. And looking forward to get your questions. Thanks.
Yeah, thank you very much, Martin, for the great talk. So maybe Volkan wants to ask the first question. I want to ask a bit more machine learning question, like for the, let's say, the partial training part. So okay, so now we learned convergence is good, but how about the like generalization performance by training a model in that way?
Yes, how is
converging faster does not necessarily mean generalizes better, right?
True. Yeah. You're right. I should have mentioned this. So all our convergence results are only on the training error. That's right. Unfortunately, I cannot say much on the test error. So I can't say much, but hopefully we behave a little bit similar. But here, yeah, all the results is only on training. Yeah.
Have you ever done any experiments on like a test error analysis?
Yes, we do. In practice, we always report the test error as well. Yes, in this paper, for example, and also in the others. So you're completely right. What matters in practice is the test accuracy. I agreed, and we do see that it usually matches quite well. Yeah. I can also say that in the last on the Byzantine training, this is also a bit interesting because there we can actually get better results if the networks are over-parameterized. So then if you have over-parameterized that you can fit everyone's model or everyone's data individually, then you can even show that this works on heterogeneous data if everyone has a different data distribution. Because the result I showed here was only if in the IID case, everyone has same data, which is of course very limiting. So if everyone has different data, this becomes harder, but then we can have a result when the networks are over-parameterized. It's very hard to have different data on every client here, because it's impossible to distinguish a client who is just very strange from data, but genuine, from a client who is malicious and pretends to have some different data. So there's kind of an impossibility result to distinguish those. But if networks are over-parameterized, then it doesn't matter. Then we can still achieve convergence. So to the good workers.
Can we somehow learn the kind of quality of each client from, I don't know, you may throw some known data and wait for the reply from each client.
That's a very cool direction.
It's a multi-unbounded problem, right, basically.
Yeah, this is super cool. So you're right. Here the decision is completely binary, right? It's a yes, no, if we exclude a collaborator or not. But it would be very nice to combine this with a more gradual weight for each collaborator, like we had in the personalized setting where we had the alpha collaboration weight. So here I would think if there might be a unified view where instead of clipping by yes, no, you could use the clipping distance to judge, to have a gradual contribution from each collaborator. So maybe the clipping or the same aggregation rule could also be used for generalization. We haven't looked into it yet. So.
Thank you very much. Yeah. So go ahead.
Thank you, Masashi. I misunderstood what you said. That's why I was. So I have two questions. So one is maybe on some of the subtleties that I missed. You mentioned some algorithms, and then you injected this sentence that, oh, the theoretical one has to do a full gradient computation. Now, there I'm assuming what you meant is that you guys somehow stress tested these algorithms in some practical setting and found that even without the full gradient computation, they perform well. But maybe in theory, you do need that full gradient computation in order to certify the rates. Is that what you meant there? Could you please elaborate?
Sure, that's right. So there's two aspects here. So one is this X here, which you have on the bottom, which means that there's two different gradients which need to be communicated. So that's one downside of this scheme, that you also need to send this, everyone at the end has to compute a gradient at X and not only at Y, and you need both on the server to do this. But this is in both algorithm variants, and so this is a small communication overhead. but still it's the first algorithm which beats this lower bound. And the second difference is what you said, that the two here are a bit different. So the full Mime on the second line has the better rate, but it actually has an additional control variate, which I didn't show on the previous slide. So there's a different correction you need to do to achieve, to learn again, it's control variate between a global quantity and a local quantity. And I have not shown that in the algorithm, but you need that, like in momentum-based variance reduction, to use that kind of algorithm, and then you get the good rate. And yes, this is more expensive, and that's the one which needs the full gradient, which is the downside. Yeah, but in practice, yes, the light one is much more efficient per step, of course, and it converges almost as good as the full one. Yes.
Okay. Well, that's a good observation. So the second question I have was the following. You talk about this personalization, and when you talk about personalization, somehow it reminds me of Masashi's talk with covariate shifts and so on and so forth. So I was thinking, have you considered the cases where, let's say you have some distribution for overall clients that are somewhat matching, and somehow we can think about this personalization problem within the covariate shift kind of framework. I think Masashi had a very good presentation.
It's more like multitask learning, right? So we have different people, but they are not completely different, but they are similar. So we want to somehow reuse data from other people.
Yeah,
so
that's
that kind of
completely right.
Learning is quite similar to, I think, multitask learning setup.
The multitask is kind of the same. Yes, it's the literature is a bit hard to navigate indeed. So because you're right, I really like the multitask viewpoint, right? It's the same as personalization. I agree. Also, the meta learning is sometimes a bit different, sometimes the same as well, right? Like, is there something that can help everybody to quickly adopt? So these are kind of the same, and we must compare to them, yes. And covariate shift, yes. So this would be more a similarity between the data, but how we use the quantities here to act is only via these quantities based on the gradients, right? So it's only the gradient similarity which we exploit to do stuff. And I mean, the algorithm I showed is not even learning these collaboration weights, right? The personalized one we just set this alpha I theoretically, right? It's just one number, so it's very naive. So there would be much more advanced algorithms which actually learn these alphas as you go on, because the collaboration weights may be changing during training. So that's what the CI is doing a little bit. But we have not looked at you were kind of mentioning what is the reason that the gradients are different. So there might be clear patterns in the data. Is it coming from the label or the shift in the X or so? So we have not thought about that yet, but it would be very interesting to do.
Yeah. I think to me this is also a very interesting problem. So we're also thinking along these lines. Maybe I'll ping you later. Any other questions for Martin? Okay.
Yes, no further question. Then it's exactly 1 hour now. So let's finish the seminar. So thank you very much, Martin, for the great talk today.
Thanks, everyone, for joining.
Thank you, Martin.
Okay, so as I announced in the beginning, so today we had Martin Jaggi as a speaker. So the next time, so December 15th, the same time, so we have Hidetoshi Shimodaira from RIKEN. So then January 19th, so Michelle, I can't pronounce the name.
Michele Ceriotti.
Thank you. So on January 19th, then February 16th, Naonori Ueda from RIKEN. So we are looking forward to your joining again to those seminars. So thank you very much for joining today. So that's the end of the seminar. Bye-bye.